let's talk about Raman. Spectroscopy can be performed in a number of different ways. You can look at the absorbed light, right? Absorption spectroscopy, like you usually do in UV vis, the transmitted light, right? Or scattered light. And what do we mean by scattered light? That's when photons come in, they collide with an atom or molecule, and then they change directions, right? That's scattering. We've always been talking about transitions between real states. Real states they're the states of the isolated molecule. And today when we talk about Raman, we're going to introduce this idea of a virtual state, a state in the molecule that only exists when it's being perturbed by the optical field, by the electromagnetic radiation, right? And these virtual states play a role in what we call nonlinear spectroscopies. These nonlinear spectroscopies are often encountered when we do laser spectroscopy because of the high intensities we can get from lasers, right? So linear spectroscopy, what do we mean by linear? The response of the system depends linear on the light intensity. So UV vis absorption or fluorescence, the way you've done fluorescence on the eclipse, right? Those are linear spectroscopies. You get more fluorescence if you add more light in as excitation, and you get a linear response, a first order response. Nonlinear spectroscopies are when the response of the system depends on some higher power, squared, cubed, something like that, of the intensity of the exciting light, right? And often the number of photons involved is equal to that power, the order of the intensity dependence. A second order power dependence often means that 2 photons are involved, etc. Right? Okay. The Raman spectroscopy that we'll talk about today is indeed a 2-photon phenomenon. We'll show you what we mean by that. Okay. So in Raman spectroscopy, right? Or let's back up to what we've done already, right? Normally, if you have incident radiation and it's non-resonant, right? It doesn't match the energy of a transition, and most of it is simply transmitted. Now, a small amount of light can be scattered elastically. That's known as Rayleigh scattering. Well, that would be what you're seeing here, right? Here we have a strong, intense laser beam, and some of it is scattering off of the molecules in the air, nitrogen, oxygen that's in the air, and it's just getting elastically scattered. So we see the green light. These are both YAG lasers, very different types of YAG lasers in these two, but this is Rayleigh scattering. It's elastic scattering of light off of molecules, non-resonant light, not resonant with any transition. It's just bouncing off and being scattered into all 4 pi. The wavelength dependence of Rayleigh scattering, it is increasingly likely with shorter wavelengths, right? And this is actually what leads to the blue in the sky. The intensity of scattering, Rayleigh scattering, this just elastic scattering, when photons bounce off of molecules, it goes as the inverse of the wavelength of light to the 4th. Bluer light is more likely to scatter than red light. And that's actually what leads to the blue that we see in the sky, light that should be passing by because it's missing the Earth, but it's hitting the upper atmosphere, gets scattered by the atmosphere, and the blue light gets scattered to a bigger angle and to a larger degree, and therefore that's why we see blue from the sky. Raman spectroscopy is a type of scattering, but it's a type of inelastic scattering. And in particular, what we're looking for is we're going to go to high field strengths, high electric field strengths, high enough that those incident photons, they actually can start to leave an impression on the electron distribution of a molecule, right? And they polarize that electron distribution. All right, the size of the polarization or the induced dipole, if you like, that's caused by the electromagnetic field's electric field strength, it depends both on the strength of the light and the polarizability of the molecule. All right, so as the field strength, the electric field strength in the the photon field, right? As that increases, this polarization in the molecule increases, and eventually it forms what we'll call a virtual state. Okay, a virtual state is a state of the molecule plus field, right? It's the electric field is imprinting itself on the molecule's electron distribution, and it creates a new state, this virtual state. And as soon as the electromagnetic field goes away, that state goes away, right? But it leads to the chance for energy exchange between the photon field and the molecule. And this is really the basis of a number of different nonlinear multi-photon phenomena. In Raman scattering, right, a photon comes in that has a certain energy, given by the blue arrow in this case, right? And it interacts with the molecule, imprints its polarization on, creates this virtual state. And then the system relaxes by scattering a photon, all right? And that's the red arrow here, all right? If the red arrow is the photon that's released by the system, and oh, look, what happened between these two different photons is that the energy difference between the photon that came in and created the virtual state and the photon that went out, that relaxed it, they differ in energy by exactly the amount of one vibrational level, right? So the blue photon was not resonant with any transition in the molecule, but the energy difference between the photon that interacted with the molecule and the photon that was scattered, that is what's resonant with the molecular transition. Now, if a photon came in and it interacted with an excited state molecule in the first place and created a virtual photon, it could actually scatter away a photon that is more energetic. But again, the energy difference between the two has to be resonant with a transition in the molecule. All right, so we have two types of transitions that could occur. A Stokes transition, that's what we would normally think of as exciting a molecule from, say, in this case, V = 0 to V = 1, or an anti-Stokes transition. That's where we start off in an excited state and relax it and put that extra energy into the photon so that the scattered photon comes out at a higher energy than what was initially there. A Raman spectrum looks like this. It doesn't matter what the frequency or wave number of the photon is to start with. That's not what, it's not resonant with the transition. It turns out that the bluer the light is, the more likely it is to create the scattering effect. Oh yeah, just like Rayleigh scattering, right? The intensity of Raman scattering goes up as the inverse of the wavelength to the fourth, right? The energy of a transition is the difference between the Rayleigh line, right? That's the elastic line. That's the line that you went in with to excite the system. The energy difference between where a Raman line ends up and where the zero was, where our initial wavelength, that's the transition energy, right? That is what is, it's the difference between these two that it ends up being resonant with the transition that we excited. Okay, and we have both Stokes lines to lower energies, right, where we leave the molecule in an excited state, and there are anti-Stokes lines which go to higher energies, which relaxed a molecule that was initially excited. Laser beams can have really well-defined wavelengths and really high intensities, and they're really nicely collimated, right? You can see how well collimated this beam is, right? In Raman, you don't want to see the Rayleigh line, right? This line is huge. The intensity is going off scale here compared to these ones. That's not what you want to see. Basically, the way you usually set this up is you have a laser as your source, because you need a well collimated and high intensity and well-defined wavelength source, right? And we're going to detect at 90-degree angles to where the sample was, right? We don't want to see the exciting beam. There's going to be Rayleigh scattering that goes all around into 4 pi radians. There's going to be Raman scattering that goes all around into 4 pi radians. And so what we need always then is either some filters or a grading spectrometer, and then just look at the Raman lines that will be resonant with the excitation that we're looking at. You can do this for any kind of excitation, electronic, vibrational, rotational, in principle, okay? But the reason why it's difficult is because the narrow spacing between the Rayleigh and Raman lines, right? Back here, right? If this is rotational, remember those diagrams we had of rotational and vibrational. You know, if you're looking at a rotational line, you're right next to the Rayleigh line. Vibrational lines can be spaced much further away. So it's much easier to get either filters or a grading in here that can separate out the two. Why do you see delta J equals 2 transitions in a Raman event? And here we've got 2 photons. We got one up, we got one down. And because of that, again, conservation of angular momentum, we're going to worry about 2 units of angular momentum, right? And so since it's 2 photons, one up, one down, we can change the rotational quantum number by 2 units. When does Raman work, right? After we figure out we can have this phenomenon, next we want to figure out what the selection rules are, right? So let's expand out in terms of the molecular displacement again. Oh, good old Taylor series, right? So let's do that. This is the polarizability of the molecule, all right? So there's a constant plus the derivative with respect to the change as we expand the bond, right? As we make a vibration, times x, the coordinate along the internuclear axis, right? Pop that in there. Oh, this is a constant. If that's a constant, we pull it out. And then this integral has got to be not equal to 0. Well, that integral is going to not be equal to 0. That's for delta V equals plus or minus 1 for a harmonic oscillator. That's no problem at all. Oh, but this derivative must not be equal to 0. Okay. In other words, you need a change in polarizability, right? The derivative of polarizability with respect to x has got to be not 0. There needs to be a change in polarizability as the vibration occurs, right? Now, a way to, well, how does polarizability change, right? Well, it turns out in point group symmetry, the vibration has to transform as one of these quadratic elements, right? X squared, Y squared, Z squared, or the cross terms, right? Those are the Raman active modes. All right, so if you look at these point group tables, right, they'll always tell you, so over here, there are these elements, and then whether they're symmetric or anti-symmetric, whenever you do this, in those tables, they'll always tell you how the coordinates X, Y, and Z change under a translation, or how these quadratic terms change, right? And so in order for a mode, a vibrational mode, to be Raman active, it has to transform as one of these. So if you know the symmetry of the vibration, you can tell whether it's going to be Raman active and along which axis it will be Raman active by looking at the point group table. The Raman effect, it's a 2-photon event mediated by a virtual state, a state that is generated by the action of the electric field of the molecule, or electric field of the photon field on the molecule, right? Both the up and the down transitions, 2-photon transition, right? And that's what leads to these delta J equals plus or minus 2 allowed. That is, you see O and S branches, or if you get plus on one and minus on the other, you actually get the delta J equals 0 transition. So you can see a Q branch in Raman spectroscopy as well, right? Some modes are Raman active, some are IR active, and there are modes that can be both, right? If you have a center of inversion, turns out they won't be both, right? And in molecules with a center of inversion, you have to do both IR and Raman to pick up all of the modes if you want to observe all of the modes of a molecule. Okay. Again, anharmonicity can lead to some weak overtones. Raman's already weak, so seeing overtones in Raman, it takes a very intense source.